for the remainder of our unit on fluids, we really focus on fluid dynamics. That's going to be where we actually have fluids that are moving throughout a pipe or throughout a system, and we study that motion of fluids and understand how the pressures and how the shape of the fluids or the shape of the containers that the fluids are actually moving through affect that fluid's motion. The first thing we need to focus with fluid dynamics is what's called flow rate. And that's where we understand the mass of a fluid that's actually moving through an area at a set time. So if we take this shape here and we say, let's look at this area right here, we'll call this area 1, and we want to know if the fluid is moving from left to right, what's the mass of fluid that's actually going to be moving through that area at any given time. So we would define flow rate as the change in mass over the change in time that moves through my system. Within fluids, again, mass can be very challenging to determine, so we can calculate mass by the density times the volume, and volume as well, when things are moving, can be very challenging to calculate. We can actually calculate volume in terms of the area times the length. In terms of from starting at this location to when it hits area 1, that is going to be some set length that it has traveled. Obviously my area has not changed in this circumstance, it's changed definitely when we get down here to the bottom, but if we're just simply looking at area 1, this length divided by time is basically a distance divided by time. That tells us a speed or a velocity. So we can rewrite flow rate as the density of the liquid times the area times the velocity. So that's a way that we can actually measure the mass per unit of time or per second that travels through any system if we know the density of the liquid that's moving, the area of the container that it's moving through, as well as the speed or the velocity of that fluid moving. Now, what we know about flow rate is that when we're moving through a system, that rate of flow must remain constant. We can't have less mass traveling through here than here because then they're going to create gaps within our flow. So if we look at area 1 versus area 2, how could we determine how things are going to move from area 1 to area 2? Well, if the flow rates must remain constant, that means that the density, area, velocity at position 1 must equal the density times the area times the velocity at position 2. If that's true, then density can go away, and we're left with the relationship that area times velocity must also equal area times velocity. So if we try to calculate the velocity as the liquid is traveling through area 2, what we can see is the velocity at position 2 is going to equal the velocity of position 1 multiplied by the ratio of the areas, area 1 divided by area 2. Because area 1 is greater than area 2, this is going to be a ratio that's greater than 1, which is show that the velocity through 2 is going to be greater than the velocity at 1. So this is showing that our liquid is actually going to be speeding up. So as it moves through our container this way, we're going to have a higher velocity through area 2. And that should make sense. Because it's a smaller area, we need to have a faster velocity for essentially the same amount of liquid to get through per second. So if we think about this volume of liquid, to get through area 2 would maybe be this same volume. Well, this place, it would have to have a greater velocity to get through that as opposed to area 1 because it has such a smaller hole to actually get through.